Hello. This week we introduced one definition in calculus, which is a limit, intuitive definition of limit, and also we have introduced a theorem about limit on functions. Okay, so let's review what we have covered. The intuitive definition of limit. Okay, this is about limit at point. Okay, about limit at point. You can find this this definition in section 2.2 if you're using edition 2. Use 8th edition, and the 7th edition. I think it's about the same place. Okay, so let's write it down. So we try to understand the words. Okay, a lot of time when we study mathematics, we need to know that we need to focus on the definition and theorems, and we use those definitions and theorems to guide our steps. Okay, so I'm gonna copy the question, copy the definition. Okay, when you listen to the lecture, you also write it down, just like you're in the lecture. Suppose function f of x is defined when x is near the number a. Okay, so what does this mean? This means, okay, this means that f is defined on some interval that contains a, except possibly at a, which means that it may be defined at a and maybe not defined at a. But whether it is defined at a or not, it doesn't matter. Then when we write the notation, okay, then we write, okay, understand this is an intuitive definition of limit. When we write something like this, okay, limit, okay, that's a short for limit. And x approaching a. Okay, and we have a function here. It equals to a number L, and we have a way to read it. And the way we read it is, and to say, the limit of f of x as x approaches a is L. That's how we can read it. Are there other ways to read it? Of course, we can read it, say the limit of f of x is L as x approaches a. Okay, so there's another way to say it. Okay, so This is not in the textbook, but I'm going to write it down here. It says the limit. Okay, we're talking about learning using the language of mathematics, and here it comes. Okay, the limit of f of x, the limit of f of x is L. Okay, as x approaches A. Okay, x approaches A. So these are the different ways to say it, and there are other ways of saying it as well. So whenever you see this notation, you would say the limit of f of x as x approaches A is L, and then the limit of f of x, or the limit of f of x is L as x approaches A. There are also some other shorthand notations you can use. You can say f of x, okay? You can also say, using shorthand notation, okay? You can say f of x approaches L, okay? This is the time you can use arrow. In fact, you cannot use equal sign, okay? As x approaches A. As x approaches A. Okay, so that's another shorthand notation you can use. And of course, you can write it down just like that. Okay, you cannot write f of x equal, if you remove the limit, right? You can't do this, okay? You can't say, say removing this. You can't do that. Okay, even if you attach x approaches A, don't do this. You will have to use arrow. You will have to use arrow here. Okay, so this will be the proper way to express it. This will be the proper way to express it. Okay, so we need to understand approaching a number. So now from functions perspective, okay, we remember the definition of function. Okay, first, we know that a function is a rule, right? So definition, recall the definition of function, right? A function f is a rule, okay? And this rule is specified. This rule does what? This rule assigns each input, okay, each element, whatever, each input exactly one output, okay? So each input, so we're gonna have some example, okay? Each input x exactly one output f of x. And we know that according to the rule, we will have domain and range, okay? If we draw a picture how it works, okay? So, hold on. So x is the input, right? And there's a function here. It produces an output. The output is f of x, okay? So what does it mean that x is approaching A? Well, x approaching A means that when x approaches A, okay, so x approaching a number, to approach a number A may or may not be in, may or may not be in the domain, okay? Because in the statement says, f is defined on some interval that contains A exactly except possibly at A. So x is approaching A. Okay, so that's the concept of input. Okay, but A may not be Okay, A may not be in the domain. Okay, where A may or may not be in the domain of F. Okay, we're going to revisit these concepts, right? So when we do that, okay, you can see one number approaches another number A, and it's a dynamic process. It's a moving process, okay, getting closer and closer and closer and closer, but never touched it, never touched it, okay? When X is approaching A may not be in the domain of F, but F of X approaches a limit, a finite number. So this is the definition in conjunction with the definitional function and what it is. Okay, so let's look at some examples. Okay, the example we have done in class is this one. Okay, so we have limit. Okay, limit X approaching 5. And here we have a rational function. We have X squared minus 6X, I believe, right? 6X plus 5. And the denominator is X minus 5. Okay. When we look at the function here is F of X equals to this rational function. Rational function is one polynomial divided by another polynomial. Okay, and in this case, if you look at the domain of this function, okay, domain of F is all real numbers but 5. Okay, all real numbers but 5. So we're going to write it as X is not equal to 5, meaning, okay, means, right, the domain include all real numbers. Okay, the domain includes all real numbers except 5, because 5 will make the denominator equal to 0. Right, when we look at the definition of the limit, you see F of X is defined everywhere but 5, right? So it's fitting for that description. F of X here is defined near the number 5, right? So if we apply the definition here, right? If we apply the definition here, right? Suppose F of X, which we have F of X, is defined when X is near number 5. Okay, this means F is defined on some interval that contains 5, except possibly at 5. Okay, it's very unfortunate this time 5 is not in the domain, but it's okay. We can still consider the limit of this function. Okay, now, when we look at the limits, we're going to use the algebraic way to handle the situation, because we know that X is approaching 5, but it is not 5, right? And because X minus 5 is not 0, because if X is not 5, X minus 5 is not 0. So if X minus 5 is not 0, maybe we can do some algebraic manipulation, right? So that's what we're going to do. And it turned out we can factor the numerator, okay, into X minus 5 times X minus 1, okay? And because X minus 5 is not 0, so we can apply mathematical principle number 1, right? X minus 5 will be reduced, So as a result, we will just have X minus 1. Whoops. Okay, we just have X minus 1. And then what do we do? Okay, this week we learned one definition and we also learned a theorem. So I'm going to put that theorem right here. Okay, that important theorem, we call it direct substitution theorem. Okay, direct substitution theorem. Okay, so let's write it down. Theorem. Substitution. Direct substitution theorem. What does it say? It says if f is a function, that is a very special function. If f is a polynomial, or a rational function. Okay, and okay, there are two conditions. A is in the domain of the function. A is in the domain of the function. Of f. Okay, so we can use the shorthand notation f because we already mentioned that function. Then the limit of f of x, okay, limit of f of x as x approaching a, in this theorem, a must be in the domain of f. Okay, you need to know the difference. A is just a placeholder. Remember, A is a placeholder. In this theorem, A, even though they both called A, in definition of limit and in the direct substitution theorem, this A must be in the domain of f. If that is true, then we can directly substitute A in the function. Okay. Now, we can apply this theorem to our situation right here. Okay. 5 is in the domain of x minus 1. X minus 1 is a polynomial. It's actually a binomial, right? The domain of x minus 1 is all real numbers. Then you say, how about the previous one? Well, the previous one, 5 is not in the domain. So now we have reduced the expression. We have reduced the function to x minus 1. And this new function x minus 1's domain is all real numbers. And similarly, 5 is also in the domain. So we can just substitute. A, okay? So in the theorem, A is 5. So 5 minus 1, and that is equals to 4. Okay, so we learned these two theorems. One theorem or one definition for this week. Okay, so let's look at another example. Okay, so what I'm going to do is that I'm going to bring the definition and this theorem and this direct substitution theorem along with us. Okay, so we have the intuitive definition of limit, and we also have direct substitution theorem. So we're going to apply these two in 2 questions in our homework. Okay, so let's see what's in our homework. Okay, so let me look at the questions we have. Okay, for this week. Question, hold on, I need to log in here. And then we're going to pick up some questions in our homework section. Okay, so this is our homework section. This is our homework section. We did the first one, right? Second one is similar. Third one, right? Third one is similar. And let's look at number 4. Number 4, right? Number 4, we have the algebraic part, and now we're going to look at the limit. Okay, I will have a separate lesson on the algebra part. Okay, so let's look at how we're going to find the limit as x approaching -2. Okay, x is approaching -2. Wait a minute, I think I made a typo here. It should be x plus 2. Yeah, my bad. It should be x plus 2. Okay, so forgive me. I'm going to make that a correction after the recorded lecture. Okay, so can be done. All right, so we're going to take a limit of x as x approaching -2, and the function is x plus 2 over x to the power 3 plus 8. Okay, so let's go back to the other document. This is example number 2. Okay, example number 2. So this time we're going to have limit. Okay, this time x approaches -2, and the function in consideration is x plus 2 over x raised to the power 3 plus 8. Obviously, we have to handle this situation, but once again, right, we want to take the limit, and we want to check f of x defined when x is near the number a, and a here in our case is -2. Is the function f of x equals x plus 2 over x to the power 3 plus 8 defined at -2? The answer is not. The answer is not. Okay, so we can assume this function, right? This function equals to x plus 2 over x raised to the power 3. Wait. X plus 2 over x raised to the power 3 plus 8, right? In order to determine domain, this time the domain determination is a little bit more work. It's a bit more work, right? So when we are looking at the definition and the theorem, then we will think, okay, let's see how we determine the domain. The domain, since this is a rational function, the denominator cannot be 0. So we first set up, right? So we're going to set up that not equals to 0. If x raised to the power 3 plus 8 is not 0, plus 8 is not 0, that means x raised to the power 3 cannot be -8, right? When would that happen? We can take a cubic root on both sides, if you like. Okay, we're going to take a cubic root on both sides. Cubic root on both sides. And then what do we get? The left-hand side is x, and the right-hand side, -2, right? Guarantee the denominator is not 0, then x cannot be -2. So as a result, the domain is all real numbers but -2. So we can use shorthand notation like this, right? So this means domain includes all real numbers but -2. But -2. Right? We understand that. So with that consideration that we know that -2 is not in the domain. By the definition of limit, it's okay that A is not in the domain, but the function is defined everywhere else. So there is, you know, the function is defined near -2. Okay, so f of x is defined near -2. So the question is, can we do some algebraic manipulation, right? Like the factoring technique. Well, I think we can. I think we can, right? X raised to the power 3. Okay, so let me remove this one first. Okay, and look at this, the possibility of factoring. X raised to the power 3, right? And that is equals to x raised to the power 3 plus 2 to the power 3. There's a factoring formula. You can look it up. Okay, so here I'm just going to use a result. I'm going to talk about factoring independently in another situation. So this is a factored. Actually, how is it factored? Well, there's a formula. Okay, and you can check, does it work? You can always check it if it works, right? By FOIL. Now, with this factoring going on, we can continue to simplify to see if we can reduce it. And sure enough, when we replace the denominator by its equal, we get x plus 2 as a common factor. X plus 2 as a common factor because x approaching -2 but not equals -2. Therefore, x plus 2 is not going to be 0. If x plus 2 is not equal to 0, we can use mathematical principle number 1 and reduce it. So the next step, we will have x plus 2 removed, and we no longer need the parentheses here. Now we ended up by the taking of limit as x approaching -2 for function f, now is reduced to taking limit of as x approaching -2 for another function. The question is, we're going to apply the definition, the limit of definition one more time. And maybe can we apply the direct substitution method? Can we apply direct substitution? Then you have to question, is this function defined at -2? Okay, you can try to find the domain of this function, or you can simply say, okay, I'm going to try, right? So on your scratch paper, we can just try if -2 will make the denominator equal to 0, right? On your scratch paper, you say, does -2 make the denominator equal to 0? If it's not, it is in the domain, right? So we're going to replace x by -2. Then you say, what if it is equal to 0? Then you have to use the definition one more time. You have to continue to factor it, okay? Now, when we substitute x by -2, we get -2 squared minus 2 times -2, And here we get 4, and we get another positive 4, and we get 12. It's not 0. So this demonstrates that what? This shows that -2, this means what? This means -2 is in the, -2 is in the domain of this reduced function, this new function. Oops, why doesn't come? Okay, come over there. Okay, so then we can apply direct substitution property. Okay, direct substitution property here. And then we can plug in. Okay, so the scratch paper work, I'm going to put it on the bottom. Okay, these are on scratch paper. So here you can just continue the process. Okay, you can just continue the process by direct substitution. So now you can drop the limit. Remember, in the left, you have the limit, right? You don't have the limit, right? Drop the limit and substitute it by this number, by this quantity, under 1. Okay, sorry. So in the end, we're getting 1/12. 1/12. If you look at the way we show our work, pretty much you have these considerations about domain and using the theorem. When you use the theorem, you have to make sure all the conditions are satisfied by, all the conditions in the theorem are satisfied. And it's in the textbook, it's called direct substitution property. Okay, I call it, theorem. Okay, I call it theorem, same thing. Okay, it doesn't make much difference in this case. Okay, so you can continue to do the homework. And I will do another example that we did similar things in class with H, right? So maybe we look at number 10. Okay. In number 10, we have, make sure you write it down. Maybe you want to pause the video here and try on your own. Okay. In this example, unlike in other examples, you have 2 variables, but one of the variables approaches a number A. Okay, so let's look at how we will be working on this one. Okay, so example number 3. Okay, limit and H approaching 0. And now we have a very special situation. We have x plus h squared minus 1/x squared. And the denominator is an h. Okay. We're going to take our definition and direct substitution theorem with us. Okay, we're going to need them, right? We constantly just go back and forth and check, because the process you learn mathematics at this point is you applying definition and theorem to make your case. Okay, these are your tools. These are your tools to get points. Okay, these are your tools to get points. So when you simplify, I'm going to show you there are 2 different ways you can show work. Okay, one way is that you do your work algebraically separately. Okay, so method number 1. Okay, I'm just going to work on reducing this function. Okay, we're going to just reduce the function first. How do we reduce the function? Well, this is algebra, right? So we're going to do the algebraic work to reduce the function. And the numerator, well, the denominator, you can view it as h over 1. But you don't need to do that. It just you know it. So you have one quantity, two quantity, and a third quantity. And what are their common denominator? And we decided that the common denominator is going to be x plus h squared multiply x squared. And so we apply mathematical principle number 1 there. Okay? Anything times 1 stay the same. When we are doing something like this, of course, the domain for this entire function, if you only consider h cannot be 0, right? H cannot be 0. So h cannot be 0 is guaranteed. So we can assume that, right? Now we're going to take this numerator, okay, multiply each in the numerator. Okay, we can take the denominator and multiply the denominator, right? Product of fractions. So 1 over 1, that becomes reduced. And next, we're going to take care of, you really don't have to show this step, but you may like to do it in a scratch paper, right? X plus h squared, and here you have x plus h squared. So these two makes 1. And this 1, you can omit it. Over here, 1 over x squared, and take away the 1 over x, take away the x squared. So this is reduced. Denominator, don't do anything. Don't do anything, don't FOIL this. Okay, just leave it like that. Okay. As I mentioned to my pre-calculus class students, you want to leave things in factor form. We like things in factor form. Okay, so we have factor form in the denominator already, just leave it like that. Don't expand it. Numerator is not in the factor form, but we will make it into factor form if we want, if we can. Okay, so that's what we're going to do next. Next, we're going to FOIL x plus h squared. Okay, so I'm going to put a bracket just in case I don't make any mistakes. Okay, so thinking of applying a plus b squared, that equals to a squared plus 2ab plus b squared. Okay. Be warned. Remember that common mistake we talk about in many times over, right? Be warned that is, if you drop the 2ab, you're making a mistake. Okay, so this is a plus a squared, a plus b squared equals a squared plus b squared, that's false. Okay, that's false. Okay, just be warned, okay? All right, you don't have to put the things I wrote in bracket in your work, but that's what I'm gonna apply. Okay, so that's gonna be x squared plus 2xh plus h squared plus h squared. Okay, I keep them in the bracket because I know there's a negative sign in front of it, right? I don't want to do two things at the same time, just to make sure everything is made easier for me to come back to check the work. So then I'm going to open up the parentheses, so remove the bracket, so all of these are going to turn into minus. Now I can handle x squared minus x squared. That's going to be 0, right? I'm going to factor. Okay, we like factor form. Okay, we spend a lot of time learning how to factor. So this is the moment we get to use it. I'm going to factor out the h. I'm going to factor out the h. In fact, I can factor out I can factor out negative h. Okay, I can factor out negative h. Okay, so this is going to be a plus. Plus, I'm factoring out a negative h. If you factor out h, is okay, right? If you factor out a negative h, I get this. If you factor out the h, what do you get? Well, you just have negative 2x minus h. Same thing. You want to be able to go back, check if you can go backward. Okay, go backwards. But so far, I think we got it right. And next, you see we have factor form, factor, 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 another factor, right? It's nice to have these factor forms. So now we can remove the h using mathematical principle number 1, and h is not a 0. Remember, h is not 0, right? At the beginning, 0 is not in the domain because h is in the denominator. So h is not 0. Because h is not 0, now we can reduce the h. So what do we get on the next step? We are getting negative, h is gone. Okay, but we have a negative sign on top. And this is how far you can go. This is how far we can go. I know this may look a little bit, scary. So this is the first method. We're working on the algebra part separately, and now we can apply the limit. Then, okay, so when we apply the limit, what do? Well, we have worked out all of these steps, and we got that the given function is the same as this piece. So next we can just put it in there. Don't forget to attach the limit. Don't forget to attach the limit. Right? In the algebraic part, I did not attach the limit, so I just keep going. When I have a limit attached to the function, then I will keep it attached unless I have a reason to remove it. Okay, so now we apply direct substitution property. Well, this is a function, right? Because we only consider h, so we can think of x as a number. Okay, we don't have to worry about. In terms of h, the denominator contains h, and this is a rational function of h. Okay, rational function of h is 0 in the domain. Yes. See, now if I put h equal to 0 in place, it will be fine, right? We wouldn't have the 0 denominator happens. And therefore, we can apply direct substitution method, direct substitution property, and replace h by 0. After we replace x by 0, what do we get? We just do some reduction. On the top, I will have a negative 2x. On the bottom, x plus 0 squared is just going to be x squared. And now we can even reduce it. Right? So now x is removed, simplified, so we'll end up with negative 2 over x raised to the power 3. So this is the end of the question. That's one way to show work. Another method to show work, the ideas are the same. Method 2 is that you can just take all of it. Okay, hold on. I'm going to have to make some adjustment. Okay. So what I'm going to do is that I'm going to just do them all together. Okay, forgive me, I'm going to do copy and paste. So I start with the limit, and this at this point, I'm going to attach the limit. So limit here. Okay, 200%. Start with the limit, I will attach the limit, but here I have no reason to drop the limit because I'm still working the inside of the function. I'm manipulating the algebraic part. So for all of these, the limit must be attached to it. Don't drop it. If you drop it, I will see it. If you don't have the right reason to drop it, you're going to lose point. Okay, so you must learn to express these expressions properly. Whoops. There we go. I still have the limit attached. I still have these limit attached all the way here, all the way here. Okay, you can't drop anything. And when do I drop it? When I apply direct substitution theorem. When I apply direct substitution theorem. Okay, so limit is dropped when I apply direct substitution theorem. Okay, then we dropped it. On all of these places, if you started with this limit, you have to attach the limit all the way until you have a reason to drop it. And here's the reason, of course, apply direct substitution theorem. I hope that's clear. Okay, how to show work. What do we have learned about calculus this week? And how do we apply? And when do we apply it? Okay. That's all for this lesson. I don't want to make it too long. If you have any questions, please don't hesitate to reach out to me. Thank you for watching.